Hello everyone, I'm Andrew First.
I'm Nonoy Sugitan.
I'm Dustin Wright.
I'm Lauren Woolley.
I'm Aaron Solomikos.
I'm Alex Makedonsky, and we are CEREBRO. Now, to get things started, I want to ask a quick question. How many of you guys are familiar with the term brain-computer interfacing? Got a few hands, that's great. We here at CEREBRO have done just that. We've constructed an EEG-based concentration detection system, and the way it works is we have two individual players that are going to go head-to-head in a push-of-war / tug-of-war style combat. This is going to be implemented in both software and hardware, as we'll discuss later. As the two individuals are competing, the kick of it is that the victor is determined by their individual concentration levels. So if one has more, the ball is either going to push towards them or pull towards them, or push away from them or pull towards them, depending on what game mode we choose. To break this down into 4 different sections, our project consists of an active sensor, which is placed atop the scalp of each individual. That way the raw brainwave data is collected. The data is then transmitted through our Bluetooth medium, and then resides in a host application in which the signal processing tools that we've implemented take the data and bring it into something more useful for us. The data is then transmitted to our host application, which then takes that meaningful data and then illustrates an updated image for the user, again, both on the hardware and software side of things. Before moving on, I wanted to quickly go over EEG. EEG stands for electroencephalography, and it's a method of measuring electromagnetic waves emitted by the brain. The waves that we're interested in operate at a low frequency band and a low amplitude, and as you can see in this chart, we've highlighted the alpha and beta sections because they are the ones that correlate to concentration. I know this may seem like a lot to take in, but we're going to be discussing this in more detail later as to our explanation why we chose these frequency bands. Before we get to that, however, I wanted to go ahead and bring Aaron Solomikos over so we can talk about the active sensor design.
So there are 3 main hardware components to our project. There's the active sensor for collecting brainwaves from the front of the head, and there's the EEG board for digitizing those analog signals and sending it out through Bluetooth, and there's also a physical game for demonstration. So in the signal flow of the brainwaves, the most destructive element to the brainwaves is the skin sensor contact. So we've designed an active sensor, which basically the op-amp has a very high input impedance in the gigaohm range, and when you put that in series with the 100 kilo ohm dry skin resistance, then it causes all the signal to drop across the op-amp and makes the effects of the skin resistance negligible. There's also some amplification that the sensor provides as the signal moves on past the sensor, which improves it against future noise. Some of the constraints that we had for the active sensor was that we wanted to have very few components so that there was very little noise added from the sensor, which would have defeated the purpose. And also, we wanted to have an op-amp that was good for low noise so that we could operate it off a small battery. Okay, so here you see a basic diagram of the head. These are industry standard test points that are used for measuring brainwaves. And we concentrated on FP1 and FPZ at the frontal cortex, which is associated with concentration, which was our area of interest. And there's also a reference point FPZ, which is used for the differential input of the ADC, which is also used for noise filtering. And to talk about how the signal is then further digitized and transmitted over Bluetooth, I'll transfer it over to Lauren Bully.
All right, thanks, Aaron. So now that Aaron has talked a little bit about how we're actually getting these raw EEG signals with the active sensor, I'm going to talk about how we actually get those signals to the application where it will control the game. So Dr. Osterk has sponsored our project, and part of the project's constraints was to use this EEG board, which his research team has developed. We were not directly involved in the development of the board, nor the embedded software that controls it, with the exception of some small things like changing the name of the device we were asked not to change that. But we have a good understanding of the basic components of this board. So this board is consisted mainly of a Nordic NRF 51822 Bluetooth low energy chip. It has an integrated ARM Cortex M0 microprocessor on it. And the other main component is the ADC, which is the Texas Instruments ADS 1299, which converts our raw EEG data, raw EEG signals that Aaron mentioned earlier into digitized ones, which will be sent to the host application. So here is a kind of block diagram of the order of operations to get the application running. So first, our host application, it initializes a stream of bytes, which basically are a stream of commands that basically initialize the ADC, say like start reading. So those signals are sent over Bluetooth to the Nordic chip using the Bluetooth APIs that we're provided with. Then the Nordic chip with the Cortex M0 sends those to the analog, the ADC, which starts reading in the sensor data continuously, and then digitizing that, sending it back to the Bluetooth chip, in which it will be sent back to the host application for signal processing. So why did we decide to use Bluetooth? One, we wanted to use a wireless technology because wires are kind of a hassle, and I don't like them, and I'm sure most people don't like them either. It makes it nice and clean. Another reason we use Bluetooth 4.0 is Bluetooth 4.0 LE low energy is the latest Bluetooth technology, and it's significantly less power consumption than its predecessors, which contributes to the small form factor of our design. Each individual player will be wearing a headset with the EEG board I described earlier in low power consumption. In the Bluetooth 4.0 is a very popular technology with BCI and wearable devices these days. So a brief overview of how it works. Basically, the board will say advertise some services, and within those services, say, for example, there'll be a heart rate service. Within that heart rate service, there are characteristics, which are basically channels on which data can be sent. So we're sending our data over the heart rate measurement characteristic. And so once that data is actually sent to the host application, it needs to be processed and analyzed, which Dustin Wright will speak about.
Okay, so in terms of the signal processing, there's really three main things that we're interested in. The first is the energy of the signal at certain frequency bands. The next is using those energies in some basic machine learning to classify and to predict whether the user is concentrating or relaxing. And the last thing is to, based on that prediction, come up with a level of concentration which we can use to drive a game. So, energy of the signal is very simple. Basically, we're sampling the signal at 250 hertz, which is well over Nyquist for the signals that we're dealing with, because they're down in 30 hertz, 50 hertz at the max is what we're interested in. And so once we get 250 samples, we take Fourier transform of the signal and then integrate the square of the magnitude of the spectrum between the frequency bands of interest. So in our cases, it's the alpha band, which is between 8 and 13 hertz, which is generally associated with relaxation, and the beta band, which is between 14 and 30 hertz and is generally associated with concentration and in some cases stress and anxiety. Right? And so once we get these energies, we're using them as features in supervised learning method, namely support vector machine. And the way support vector machine works at a high level is basically you get a training set of data which have a priori labels assigned to them. So we have some data where we say that the user is concentrating and some data where the user is relaxing. And then using this training set, you train the support vector machine, which essentially finds a separating hyperplane between the data with the widest possible margin. The center of that boundary is then a decision boundary where you can apply new inputs, which would be the energies when we're making predictions, and it'll be able to predict whether the user was concentrating or relaxing. All right, this is an example of some test data that we got earlier in the semester. Some pretty good test data. In training, we induced concentration, which is represented by the blue squares here. And then in the next level step of training, we induce relaxation in the user, which is the red circles here. The x-axis is energy in the beta band, and the y-axis is energy in the alpha band. So with data like this, you can see that it's pretty easy to find a separation between this data and based on new inputs be able to predict whether the user is concentrating or relaxing. Right? And this is all well and good, but just being able to say yes or no is not quite good enough to drive a game, so we had to come up with a way to get a level of concentration. Right? So we use that support vector machine to make predictions, and then we use this function here to get a level of concentration. So essentially what we do is during training, both relaxation and concentration, we get the average level of energy in the beta band for both scenarios. All right? And then when we make a prediction, we compare the rate, or we use the ratio of the new energy in the beta band versus the average energy in the beta band during the training phase, and use that as input to a sigmoid function, which basically all that does is it squashes that argument between 0 and 1. All right? And then we also apply this bias for when the user is concentrating or relaxing using that prediction. So essentially what this whole equation states is when the user is relaxing, we're going to get a value between 0 and 0.5 for their level of concentration. And when they're concentrating, we'll get a value between 0.5 and 1 for a higher level of concentration. Right? And so now that we can get a level of concentration, we need to do something fun and interesting with it. So to talk more about host application and where this is being used, I'll present No Noise Sugiton.
All right, so to smoothly integrate our software components and to have a single packaged application, we decided to develop everything under Microsoft's Metro framework. Here, we're able to take advantage of Microsoft Bluetooth API, utilize open source libraries for signal processing, and use the latest technology Microsoft has to offer for developers. Moving on to the game, we start by inducing concentration by having the users solve math problems for 70 seconds. After that, they can navigate onto the next page where we induce relaxation by having the users choose from a variety of relaxing sounds and listening to that for 70 seconds. During this whole time, data of the user concentrating and relaxing is recorded and processed. This processed data will be shown on our game interface, which is what Andrew first will go over.
So once the two users have trained, they can then go on and play the game against each other. The vertical gauges that you see here are going to be the instantaneous concentration of each user, and the ball up here will move back and forth based on the overall concentration. The way the ball moves will depend on if we implement a tug of war or a push of war, which will be up to the users. Below, you will see our actual physical game going in motion. What happens is the host application will send an 8-bit variable to the microcontroller that is within that, and the microcontroller will control the stepper motor that will move the ball back and forth based on who's winning or losing. I know this is a lot of information, so we actually have a demonstration of our video in action, and we'd like to present to you. We decided to implement a push of war in this particular video, so take a look. And even though we didn't plan on originally using the physical game that actually wasn't showed in the video, we still came out well under budget than we projected. We projected a $614 budget, but it actually ended up being $341. We did not end up buying the TI ADS development kit that we initially thought we were going to, but that gave us money to spend on the physical game. And so to conclude the budget and talk about a few of the milestones, I'll present Alex again.
Now, with a project of this magnitude, what we need to do is set up ourselves up for some plans and some goals in order to accomplish the tasks at hand. These are just a few of the tasks that we felt were most important to express to you guys today, although we had many more to come, or that already came, since we're in this time zone of December. These goals, although we were a little bit shy on our expected due dates, we did accomplish them, and we are pleased to say that on design day we will be able to have a working model to display to everyone that shows up. What we want you guys to take out of this is that we're more than just a user interface. What we've done is we've been able to express to everyone here as well as ourselves that we're able to correctly analyze raw EEG data coming from an individual's brainwaves. This data can be processed, as we've talked about, and analyzed into something useful that we can develop for future applications. The advantages for this extend to multiple fields of study, whether it be medicine, sports, or gaming, as you've seen in our application. We also wanted to make sure that our code was built and structured around reusability in mind. Whether Dr. Osterich has another team that wants to expand this project or build something completely new from it, we have usable code that's very easy to read and very easy to go forth and expand upon. This can also extend to senior design. If there's another team that's going to be performing a brain-computer interfacing project, they'll at least have this code base to get them kickstarted into something much more involved. I wanted to take this time now to just thank the electrical and computer engineering department for suffering through our bad grades over the years, as well as John, Mark, and Dr. Osterich for all their continued support throughout this semester. And now, again, we are CEREBRO, and we'd like to open the floor to some questions.